today something new, which is we know how to calculate the field of a single point charge. What if we have more than one? What if we have a number of point charges and we want to find the electric field at a location? And that's going to involve something we call the superposition principle. Which says two things. First is that the net electric field vector at a location is the vector sum of the individual electric fields at that location due to each charged particle. So it's a long-winded way of saying that if I have more than one point charge around, I can find the electric field of one and the electric field of the other just using our field of a point charge formula and just add them up as vectors and get the total or net electric field at any particular location. What goes along with this is an idea which says this: the presence of other particles does not affect the electric field, or I should say the contributed electric field due to a single particle. Okay, so what's that mean? Well, that means, let's look at an example. Let's say I have Q1 and Q2. Let's say Q1 is positive and Q2 is negative and Q3 is positive. And I want to find the net electric field at this location. Call that location A. So what this says is I can, one at a time, calculate the electric field of each individual point charge, treating or ignoring temporarily the other two charges, treating them as if they weren't there, and just find the electric field of that single point charge. So I would just say, okay, E1, I treat the situation as if Q2 and Q3 aren't here, and I just calculate what E1 is, and I would use our electric field of a point charge formula to find E1. And I know it would have to point away from that positive charge, so E1 would be in that direction. And then I move on to the next charge, and I say, okay, I ignore the presence of Q1 and Q3, and I just think about Q2 and find the electric field due to Q2, just using, again, this field of a point charge formula. Q2 would have an electric field pointing towards it, maybe of that magnitude. Call that E2. And then Q3, we'd have to ignore Q1 and Q2, treat it as if only Q3 were around to find the electric field due to Q3, and that would be pointing, let's see, away from it, kind of like that maybe. So that's E3. Let me rewrite this. And last step is just to add them up. Add up the vectors. Okay, so graphically, let's see. If I added these vectors together, I'd have, I don't know, E1. That's E2, sorry. E1 plus E2 would be something like that, and then that would give me something like that, and then add those together would give me something like that. So the net electric field due to all three of those charges would be something like that, okay, in that direction. And then I could erase the other three vectors just to show that there's really only one electric field I'm going to measure. That is the net electric field due to all those three charges, but I got that net electric field by adding up E1 plus E2 plus E3. Okay, that's the idea. Okay, so real like a simple numerical example. For we could have erase this. We could have, for example, two positive charges. Place a positive charge here and a positive charge here. And let's say Q1 is equal to 3 times 10 to the minus 9 coulombs. Let's say Q2 is the same thing, so we'll make them identical just for simplicity. And also say they're the same distance away from the origin. Let's say this is 3 meters and this is 3 meters. Okay. And I want to find the net electric field at the origin, at 0, 0, 0. Okay? So, again, without even having to do too much calculation, what do you think the direction of the net electric field is going to be? Point with your fingers. Anybody? Okay, some people pointing that way. These are two positive charges, right? So kind of like that. Yeah, let's do it. Let's follow the superposition principle. Do it one at a time. Okay? Ignore Q2 and just look at the electric field E1. What direction would that point? Point that way, right? Away from E1, right? So that E1 is going to be pointing in that direction. And we could quickly calculate this without having to do too much mathematics because we know E1 is 1 over 4 pi epsilon 0, Q1 over R squared times R hat. Well, what's R hat? What's the vector that points from the source to the observation location that lies along the positive x-axis? A unit vector pointing in the plus x direction is I, right? Or I is equal to, whether the components of I are 1, 0, 0. Okay, so we know this has got to be 1, 0, 0, right? So we have 1 over 4 pi epsilon 0, Q over R squared times 1, 0, 0. Okay, so we can just eyeball this and figure that out. So that's going to be 9 times 10 to the 9th times 3 times 10 to the minus 9 divided by the distance is 3 meters, so we divide by 3 squared, 1, 0, 0. 3 squared is 9, so we have a 9 canceling the 9 down here. We have 10 to the 9th times a 10 to the minus 9. We're going to get 300 newtons per coulomb, right? And that is E1. That's the electric field due to just that single point charge Q1. Okay? Without doing any calculations at all, what are the components of E2? 0, 3, 0, right? It's got to point away from this second positive charge. Essentially, we're ignoring the presence of this guy for right now. Just thinking about the field due to Q2 at this location. It's a positive charge, and so it points away from that positive charge. So it's pointing in the positive y direction. The charges are the same. The distances are the same. The magnitude's got to be the same, right? So E2 is 0, 3, 0 newtons per coulomb. What's E net? 330. Okay, so adding those two vectors together, I get a net electric field pointing that way, right? So that's the total electric field or the net electric field that I would measure at that location due to those two charges. And again, we can erase these just to show that there's only one single electric field that we're going to measure, and that is E net. Okay? Questions? Get the idea?